This first prototype is an adjustable and deployable tensegrity structure. It uses 3 cables and 3 electric actuators for each floor. It deploys and becomes rigid only when it is fully deployed. This property is common to space applications, such as satellites and antennas. The mathematical foundation of this work is Asur graphs. Each floor of the robot is an Asur structure, a 3-dimensional triad.
Now let us observe about the behavior of this mobile system, which is called mechanism. As you can see, when I rotate this link, it rotates smoothly. But when I rotate this link, suddenly a strange thing happens. It is locked. This spatial configuration is called a singular configuration. As we can see, the continuation of these 3 links intersect at the same point. This is the singular position. Here we can see the 3 main steps that help us to derive the main idea behind the concept of the device. The first is that every mechanism has a special configuration at which it is in the singular position. Then, when we have a mechanism at a singular position, we can transform it to a regular structure, but the structure has special properties. It has internal forces. Then, when we have a structure with internal forces, we transform it into a tensegrity structure which has special properties that we can see. So what we have here is the drawing of the mechanism at the locking position. As we can see, the continuation of the links 2, 5, and 7 intersect at the same point. Now, let us transform the mechanism at the locking position into a structure. How do we do it? We just remove the driving link and put here a pin joint. The resultant structure is a regular structure, but have a special property. It has internal forces. In this case, here we have compression and here we have tension forces. So now let us move to the third step in our process. We now transfer the structure with the internal forces into a tensegrity structure. How do we do it? We just transform these 3 elements, 3, 5, 6, into struts, and 5, 4, and 2 into cables. So what do we have? We have here a tensegrity structure that has a special property. If the tensegrity structure is at a singular position, then it is stiff and can sustain external loads. But when it is not at the singular position, then it is loose. It has several degrees of freedom like a mobile system. For the sake of simplicity, till now we explained on 2-dimensional systems. Now the device is of course 3-dimensional system, but the main idea remains. In 2 dimensions, we have that the 3 lines intersect at the same point. Here we have the 3 planes, H1, H2, and H3 should intersect at the same point. So the idea remains as it was in 2-dimensional, then it is here for the 3-dimensional system. The mathematical foundation of this work is based on theorems that are proved in rigidity theory Assur graphs and the following two papers that are going to be published this year in the European Journal of Combinatorics.
This robot, which is being developed in our lab, is capable of remaining stiff throughout its movements, unlike other tensegrity applications, like a human hand that can be flexible and rigid at the same time.
In our device, we have two types of element, as in the human body. The cables sustain the tension. The struts sustain the compression forces.
Equipped with 3 adjustable cables per floor and operated with a smart algorithm, load cells measure the tension in a fraction of a second and ensure the rigidity of the structure. We even succeeded to deploy the robot with a person on it.
The device that you are going to see has 3 main features. First, it can be very stiff. Second, it can be very loose. And it has a potential to reach almost every configuration in space.
Coiling systems and actuators allow this novel type of robot to reach a wide range of angles and heights. Each floor is independent of the other, and the robot is constantly stiff. The intention is to reach an infinite range of shapes and to adapt the robot to practical needs, such as for autonomous robots, ladder bridges, and masts. The soft rigid quality makes a good platform for imitating animals' progress, such as caterpillars.